So hi guys, welcome back. Today I'm going to solve the LeetCode Biweekly Contest 173 and all four problems I'm going to explain now. So in the first question, it is the basic reverse string prefix question. You are given with a string s and an integer k. So what you need to do is reverse the first k characters of s and return the resulting array. So you can see the input a b c d and the number of characters you need to reverse is 2. So the first two characters will be reversed, that is ba and cd. So the first two characters ab were reversed to ba and cd were the same. So similarly, if you have all three, then you return zyx for xyz. Then for hey, it is only one, so h will even though you reverse h, it will same or it will be remain same. So the result was hey, and it is given that uh, s dot length is go up to 100 and s only consists of English letters, and that this is the important condition that at least one is the length of s dot length, and k is also at least one. So you don't need to worry about k exceeding the length of string, or k is 0, or like s is empty string kind of. So this is straightforward answer, that you slice the first k characters from the string and you return that, and you just add it to the later part of the string from the uh, from the index greater than or equals to the k, and you just combine them and return that. You can see that it is getting accepted, and we can submit this. So you can see it is working fine, and then we can move to the next question. So the next question is finding the minimum subarray length that contains a distinct sum of at least k. So you are given with an integer array nums and an integer k. Return the minimum length of the subarray whose sum of distinct values present in the subarray each only counted once. Okay, even though you have duplicates, they don't count to the total sum of that subarray. Then that subarray sum is greater than or equals to k. If no such subarray exists in the total array, then you return -1. A subarray is a contiguous non-empty sequence of elements within an array, that we know that. Then so here we can see that 2 will be counting as only 2 for this subarray sum, and here we got 5 with the 3 length, which is greater than 4. So we have 3, minimum of 3 here, and we have 1 that is also greater, but we have already find 3. So 3 is the of minimum length we have seen till now, starting from the 0th index. If we start from here, we find we only, if it is 2, it is not greater. If it is 5, it is greater than equal to 4. The minimum length we found is like 2. Now we update the minimum length to from 3, and move to here also, it is also 3, which is greater than 4, but we already found 2. Similarly, if we start from 3, we'll find 2 here. So yeah, like we don't have a value that is greater than 4, greater than or equal to 4. So 3 is not greater, and 1 is also not greater. If we combine both of them, it will be equal. So that is also 2. So every time we only found 2, that is the answer. So that's how we can find the subarray which is greater than equal to the limit k with the sum. But in this constraint, we can see that the length can grow up to 10 power 5 if you stick to this checking every possible pair of uh, indices as a edges, and finding the subarray sum in them, and updating the minimum subarray length. it will be an of, it will take time complexity of, like if you take brute force, you will be taking of n square time complexity. that that is not feasible. We can do better than that. So what we can do, think of sliding window here. Like if you find there that the sum is greater than, yeah, or equal to this limit, you just need to move one index forward to find that 2 3 is also greater than or equal to this limit. Then you can update that 3 to 2 and you move one more here. When it fails, you expand the right side to find that 3 1 is also greater, and then you to remove this 3 and you find 1 that is lesser, and you can expand. There is no expansion possible here, and you reach the end. So then you will return the possible was 2. But to handle this distinct values, we also need a hash map to find to have the count correctly, like how many twos are present in the current subarray. If they are more than one, we still count the sum of, like we still don't update the sum yet. And if they are only one, like here we update the sum. Like if we are at 2 and 3 and we are removing 2, we will be left with only 3 and the sum will be 3 only. But if we are starting from 2 to 3 and removing 2 from here, we'll still have the current sum 5. So to handle that, we can use a hash map. So using a sliding window and a hash map to solve this. Okay, so first we need to find the length of nums. I have a length of nums. I'll take the result as n plus 1 for now, to update it in the iterations. And if in the end also I still have this result not updated to some value less than or equals to n, I'll return -1, because I'm taking this for that reason. So if there is no such subarray exists, I would still be having the result at n plus 1, which is greater than n. That is not actually possible. So I will return -1. Okay. Or also you can take int max as well. That is not required here. That's why I'm taking n plus 1. And then I'll use hash map for that, and current sum to store the current sum of subarray. Then I'll iterate. We also have the pointers, right? We'll have the left pointer pointing at 0, and we'll move the right pointer from 0 to n plus 1. Because why? Because we also need to calculate the subarray, possible subarray with the length which is ending at the last index. So then we need to calculate the length of subarray which is ending at which is ending at last index. So for that reason, we need to go to the right pointer to n plus 1. Then we check while current sum is greater than or equal to limit, then you can remove the left pointer forward, right? So what you can do is, like, cache of, you can reduce the count of that value in the cache. The cache of terms of the pointer at left was reduced by 1. Okay. Then if cache of this nums of left pointer becomes 0, so that there is no more twos or threes or some value is no more existent in the current cache. So what we do is like we update the current sum there. Otherwise we already have one, so that we have some duplicate value inside cache, so we don't need to update the sum that we discussed earlier. So current sum minus nums of left, and we delete this entry from cache because we don't have that value. It is optional. We can also leave it there itself, but to avoid any unnecessary things, we can remove that. And after removing that, we can check for the updated length. The updated length would be okay, updated length is like, or we can also use directly inside this, and we can update it. The result is already lower than the current subarray length, then we don't need to update that. That's for that we can use minimum of the current result we have seen yet, and also the right minus left pointer. So we are at here 3 and the left pointer is at 0, so 2 minus 0 would be 2 here because we removed at 0, and we update the left pointer. Okay, and yeah, we updated that. Then okay, like if right reaches the n, we can break this. We don't need to move, like we are at the fourth index, like 0 1 2 3 and 4, like length is 4, right? So when we are at the fourth index, like calculate this updated length, we are here. Other than that, there is no reason going below than that. So if we are in middle, we are going to update this, that cache of nums of right will be, by default it is 1. If it is already existing, we will increase that by 1. Cache dot get out nums of right, by default it is 0. If there are already exists, take that value and increment that by 1. Okay, and if cache of nums of right equal to 1, so that if it is equals 1, so that is it is newly added to the subarray, then what we'll do is like we'll update the current sum, like a new element was added to the subarray, and we'll include the sum nums of right, and we will return the result. So you can check n, return res if res is less than equals to n plus 1, or if res not equals to n plus 1 is also fine, and we'll submit this. Yeah, we can see that it is working. So the third question is finding a maximum value in a constrained sequence. So you are given with an integer n, a 2D integer array restrictions, and an integer array difference of length n minus 1. Your task is to construct a sequence of length n denoted by a of 0 to f n minus 1, and that satisfies the following conditions: that a of 0 is must be 0, all elements in the sequence are non-negative, and for every index I that is greater than equals to 0 and less than n minus 2, having absolute difference of the current index with the next index would be less than equals to difference of that index. We are given with an integer array difference here, that would be this condition. for each restriction of I, the index and max val, we are given with the restrictions integer array, 2D integer array, which is having index and max vals. The value at that position index in the sequence must not exceed max val. Okay, that a of index less than equals to max val. So your goal is to construct a valid sequence that maximizes the largest value within the sequence while satisfying all above conditions. So return an integer denoting the largest value in such optimal sequence. Okay, let's see a quick example here. We are having an input with n equals to 10 with restrictions of that the value at index 3 having only one, restricting it maximum value to be 1, and also at index 8 the maximum value it is restricting at 1. So the difference between the 0th index and the first index would be maximum of 2 absolute difference. Similarly, for all the following indexes, this is the absolute difference maximum values possible. So we can start with 2 here, as it is greater than the difference is 2. We can take -2 to +2 possible values here at index 1. We can take maximum value because our goal is to maximize the largest value within the sequence. So we'll take 2 here, and then another the next difference is 2, so we can add 4 here, and the difference is 3, and the restriction is 1. So you can reduce 3 here and to reach that restriction 1, and again you can start from here and you can have that it is given that you can have a maximum difference of 4. So from here you can go from -3 to +5, but you need to take 2 here. Why? Because you need to match here the restriction of 1. So after seeing this uh, explanation, we'll think of finding the solution with the DP, taking all possible differences from that for that index, but uh, that would be not a great solution, because we can do this solution in a greedy way. Think of that, like let me take a result array of size n with all max values, a float of infinity max values with length n. Okay, and we have this condition s of 0 plus 0, and we all have restrictions. What we can do is, like, we put the restriction values, the maximum values possible in the maximum possible restricted values in those indexes, and then we can maximize these differences. In that way we can find this we can recreate this sequence. For that, for index and then restrictions. So here finding that greedy solution would be better than a dynamic programming solution is like the solve for this problem, finding the solution and solving this. That is the DSM mastery. Okay, here 3 and 1. So you have 3 at index 3 and you have 1, right? So rest of that index would be the min of, if it is already minimum, then you even the restriction means that you can be minimum lesser than that. So if it is already minimum, then you don't need to update it. If it is greater, you update that. Okay, then we have the current result with 0 here, 1 here, and 1 here, and remaining all with int max values. Now what you do is, like, you can put all the maximum values possible with all these differences from the left side. For 1 to n res of I would be min of res of I, and res of I minus 1 plus difference of I. I minus 1, okay, because this is for difference of 0 and 1, okay. Then we'll have values like 0, 2 and 4, and it is 1, and it is 2, and it is like, it is not 2 here, it will be 1 and plus 4, that will be 5, and this will be 10, and this will be 11, and this will be 1. So here we are failing, like the condition between this, the difference between them should be 1, but we are having the difference of 10. So what we need to do is, like, we need to iterate from the back as well. We start from the last index, we move until the last before index, or also you can move to the last index as well. There is no restriction on that. And then res of I would be min of res of I and result of I plus 1. Okay, you need to start from n minus 2 here, because you are using a result of I plus 1 plus difference of I. So now we are having this 1, and then we are having here 1, and this is 3, right? So we'll start from 3 and we'll leave 1 here, and then this will be because it is 1 restricted, it will be 1, and in this way you will have the max at 6. You need to return the maximum value we have seen in the result. So this way you have the time complexity be of n, because we are iterating over the array of length n constant number of times, so the time complexity would be O of n, and also space complexity would be O of n, because we are using the result array. Yeah, on it. Yeah, we can submit this. Yeah, so it is working. The fourth question is counting the routes to climb a rectangular grid. Okay, you are given a string array grid of size n, where each string grid of I has a length m. The character of grid ij is one of the following two symbols, that is either the dot, that is the cell is available, or the cell is blocked. You want to count the number of distinct routes to climb grid. Each route must start from any cell in the bottom row, row n-1, and end up in the top row, row 0. However, there are some constraints on the route. You can only move from one available cell to another available cell. Okay. The Euclidean distance of each move is at most d, where d is an integer parameter given to you. The Euclidean distance between two cells, row 1 column 1 and row 2 column 2, is We know that square root of row difference of rows and difference of columns squared. Each move either stays on the same row or moves to the row directly above. You cannot stay on the same row for 2 consecutive turns. If you stay on the same row in one move, you should definitely move to the next row above the next move. So the answer of number of routes in the possible way can be grow very large, so you can return it modulo. Okay, so if you see the grid with the 2 availables on the first row, top row, on the bottom row, one blocked and one available, and the distance is 1. What you can do is, like, from this available row you can jump over to the cell that is above that and move to the left. Also you can, that's like you can move slightly vertical to the top row, and also you can move to the top row, and you can move one time horizontal to the other available in the top row. Like, from 1 1 position you reach to 0 1, and from 1 1 you reach 0 1, and from there you move to 0 0. That are 2 possible ways. Okay, here we can see, we can understand the explanation here. That is the same, like the distance between them is 1, is less than equals to the distance, given distance 1. So similarly here, if it is given as distance 2, we are having 4 output, because from this previous row, which is at 1 1 position, you can directly move to 0 0 and 0 1. So after directly moving to 0 0, you can stay there, and also you can move to 0 1. There are 2 cases with the 0 0 involved. And if you move to 0 1 first, you can stay there at 0 1 0 1, or also you can move to 0 0 from 0 1. There are 2 more cases. So total 4 ways to climb the grid. That's what this is saying. And so if the only block is blocked and you have 750 Euclidean distance possible to jump, but there is no more available cells, so output is 0 here. And here only one row, you are on the top row, if the distance to jump is 1, so you directly stay here without any moving anything. That is one possible way. And here also you just stay here without moving. From here you move to here, and from here you move to here. That is 4 possible ways. That is it. So this is a question. For this question, what I'm thinking is, like, for any particular cell you are in currently in a row or in a column, you can jump to available places in a two you can reach that cell in 2 ways possible. Those 2 ways were, you can directly arrive from the vertically the below row to the current cell, or you arrive through a cell which is in the same row. Like, you from the below row you can move to the upper row of any possible which is lying inside the Euclidean distance possible, and from there you horizontally move to this current cell that we are looking at. Those are the 2 possible ways to reach the current cell. So for that, what I'm doing is, like, we have the mod, and we have the rows, and we have the grid, like we have the columns. So these are the functions, helper functions I wrote for the later use. I'll explain that. Before that, in the last row, like we need to start from iterating from the last row until we reach the top row. That is, in the last row, if it is available, we already have one possible way to reach that, because we can start from there. Else, zero, because you cannot start from there, so there is no ways. So you put zero there in the last row for this, and you find the vertical limit, like how many cells you can jump in the next row, in the row that is above the current row. So for that, you have one up. You need to move one. You have the difference of one for rows. Like you are the current row, and you are moving to the row -1. So that will have absolute difference of 1. That will be squared. And we are finding the dx square, and the square is less than equals to d square. Like we have the d given, so that it lies in the Euclidean distance. So for finding dx, the dx would be d square minus 1 square, that is 1, with the square root. So you find this dx, that is vertical limit is square root of d square minus 1. Okay, for that you have vertical limit. So how many cells you can reach in the next row? Like when you're jumping, you can reach that many rows, and from that many rows you can move horizontally as well. That is second case. But for the first case, how many rows that you can, how many cells you can move to in the next row? Then you find the prefix sum, because we are finding the prefix sum for all the cells in the current row. Like prefix sum stores sum of array of 0 to array of I minus 1 in that current row. You calculate that. We start with zeros, and for n range of columns we increase that prefix sum. You know prefix sum, right? Yeah. You'll update the total ways possible to that row at that current column, and always use this mod without exceeding the limit. And then you return that, finding the prefix sum. Similarly, when they ask for query to find from left to right, I'll explain this. Before that, okay, like you have prefix sum now. Get prefix sum of dp. Like we are at last row now. Here we are at last row, and we are starting from the last row to going till 0. We are reducing each row one by one. We are calculating row wise operations, and for every row what we'll do is, like for say in range of columns, if that cell is blocked, we'll just put it 0 and continue. Else, the total ways would be like you can reach there from the horizontal as well. From how many horizontal possible? That the distance would be, the difference of rows is 0 here, because we are on the same row. So the distance of the columns would be the distance given d. So you can move either to left or to right, because absolute difference would be less than equals to d. So you have c minus d to c plus d possible ways. If you can reach the cell which is at c minus d, and all of them ways you can jump to the current cell, right? So that's why we can calculate all the possible ways here. That's why I'm using this query here. So when we ask query, what we'll do is, like we will first we check if they are in the bounds or limits or not. So the L would be, the left would be max of 0 and left. If it is going beyond the 0 to the left, then it will shred it down to 0, and the right is also same. If it is going beyond the columns -1 and the index greater than the possible, then it will be reduced to that. And if L is greater than right, like if the length is the left side is greater than right side, there is no possible ways, then we'll return 0. Else what we do is like we have prefix sum, and we use that prefix sum to find the number of ways we have to count this middle query, like r plus 1 to the length, the right plus 1 would give the number of total number of ways of sum of the array till r, right? So we'll reduce, we'll subtract the number of ways to reach L, to reach before L. So we cut off the we reduce the number of ways that are not possible in this subarray, which is from C minus D to C plus D, which is from left to right. So that is the query, and we have the total number of ways here. We'll put that in our current row total ways. We are finding horizontal ways now. That is here. And if we reach that top row, what we need to do is like return the total ways possible. That is sum of total ways by mod. But we are not at the top row. So what we need to do is like we need to calculate for the next row here. For what is the next row? We have this p total, that prefix sum of total ways. We finding the prefix sum for this total ways we just found here, and then the next TP would be like the next row of possible ways would be 0 multiplied by columns. I'm initializing that, and then for each column in columns, if that row of that set in the next row in the next row, if that cell is blocked, you just update it with 0. There's no other way that you enter that blocked cell. Else, if it is not blocked, that would be the query of p total minus c minus vertical limit to c plus vertical limit, because I'll just because like you have 4 and you have 4. So for calculating this particular cell right now, you can reach from here, directly move top, or from you can directly move top if it is in Euclidean distance circle. That's why we are calculating this vertical limit. That row difference is 1 and the column difference is some dx, and then that square root will be less than d, then we can reach that. So that's why this is vertical limit. So the current cell here, we are at this current cell, this is RC, next row, next column, we are at this cell. We will look for vertical limit, c minus vertical limit, like from here to here, all three cells can jump directly to the next column. That is vertical limit. So that's why we are using this query of finding total ways to reach this next column from this current cell to vertical limit, and then we update the current cell. So similarly, we will find the horizontal ways to move in the next column as well, next row for all the cells, and then we'll find the next rows possible ways to reach each cell until we reach the row 0. Then we don't then we'll calculate the horizontal ways as well. When we are at the row 0, we need to calculate the horizontal ways, and then there is no more rows above that to calculate, so we'll calculate the sum of total ways. That's the solution here. It is a pretty good practice for dynamic programming and thinking about the matrix moving and calculating the Euclidean distance, and the logic is should be sound to solve this problem. Okay, I tested this previously, it is working. Okay, then we can submit this to see how it is working. on the global server. Yes, it is working fine, and it is also beating 62%, which is good. Yep. That's today's biweekly contest 173, all 4 solutions. Let's meet tomorrow with few more LeetCode problems. Thank you for viewing.